Or just whatever number you find for something.
Okay. Do we finish number 4 on page 13, or did we do part A? We did. Okay. All right. So okay. So I'm gonna pick out some more problems for us to try. Let's go to page 14. Yes, I think part E is a bit more challenging here. So I'll work through part E with you, page 14. Okay, so part E says cotangent squared minus cosecant of x is equal to 1. We talked about how it's easier to go through factoring if everything's in terms of one trig function instead of split between the others. And so there's a special relationship between cosecant and cotangent, and that's going to be in the form of, excuse me. Okay. So 1 plus cotangent squared x is equal to cosecant squared x. So I talked about yesterday how really the only identity you need to know is sine squared plus cosine squared equals 1. And that is partially true because if I have sine squared plus cosine squared is equal to 1, there are 2 others that you can get to without just being able to derive them. And the one that we're using is this 1 plus cotangent squared equals cosecant squared. So if I simply divide everything by sine squared from the one that is easiest to memorize, we can arrive at a variation. Right, because sine squared over sine squared is 1, cosine over sine is cotangent, and then 1 over sine is cosecant. So we have an identity that relates cotangent and cosecant, and the advantage here is I have a way to change that cotangent. So I'm going to play with that cotangent. So if I solve for cotangent squared, I get cosecant squared x minus 1. So now I have a substitution for cotangent squared, and then I can get everything in terms of cosecant, and that will kind of help me move forward in the problem. So here's my substitution. I'm going to replace the cotangent squared x with cosecant squared x minus 1. So now everything's in one one trig function. Let's bring everything over to one side. So I'm going to also rearrange it. Highest degree first. And if I subtract 1 to the left side, minus -1 minus 1 is -2. So I want us to be able to recognize this as a factoring problem. Do you see how this is a kind of a variable squared, and then you have a variable to the first power, and you have a constant, right? So this kind of resembles x squared minus x minus 2, right? So one suggestion that I had last year when we were in this section was create a simpler factoring problem if it helps you, right? So if I can factor this problem, then I can make a substitution back in terms of cosecant. Right? So I know that x squared minus x minus 2 is the same thing. Factored form would be x minus 2, x plus 1. So now that I have my factored form, I'm going to bring back my original variable, cosecant. So cosecant x minus 2. Again, we're on page 14 here, part E. Right, cosecant x plus minus 2, and then cosecant of x plus 1, 0. So you don't have to go through the variable x if you don't want to, because if you understood that this represents x, then you can just go from here to here. But if it helps having this middle step, then I think that sometimes visually more helpful for students. So now we have our factor form. We have 0 on the other side, so that's perfect. We can set both equal to 0 and then solve for x when we look at unit circle values. So cosecant of x minus 2 equals 0. Now, it may not be very apparent as to what cosecant of, what x value will allow cosecant to be 2. So I like to think in terms of sine and cosine if I can. It feels more straightforward. So what if I just flip both of these, right? I can take the reciprocal of cosecant, which I know is sine. Take the reciprocal of 2, which is 1/2. So it feels a little bit easier to think in terms of sine instead of cosecant. And this feels more straightforward because we know with our unit circle values comes more easily to us. So sine is equal to 1/2 in that pi over 6 family here. So x equals pi over 6. And then sine is also positive in the second quadrant. So 5 pi over 6. Okay, next up, cosecant of x plus 1 equal to 0. I can subtract 1 from both sides. So again, I like to think in terms of sine if possible. So I'm going to flip that cosecant, make it sine. Flip the -1. The -1 in the denominator will still give me -1. So just thinking in terms of sine. When is sine equal to -1? 3 pi over 2. Do we have 3 solutions? Part G, any questions here? Part E. Part G, sine x equals cosine x. The trick here, I mean, this is, if you look at this, you're thinking, well, there's not a whole lot that I can do, no identities to play with here. But the trick here is I can try to get cotangent to show up, because I know that if I can get sine over cosine, that is the same thing as tangent. So the trick here is if I can divide both sides by cosine, I can present a different form that may feel a little bit easier. So sine over cosine we know is tangent. Cosine over cosine is 1. So sine equals cosine is the same thing as tangent of x equals 1, but it just feels easier to think in terms of unit circle with this, right? So what x will cause tangent to be equal to 1? If we look at our unit circle, tangent is sine over cosine. So wherever my x and y are the same, it's going to be where tangent is going to be equal to 1. And so that's going to be at pi over 4, right? Pi over 4, my order pair is root 2 over 2 and root 2 over 2. If I divide those two, they cancel out. So x is equal to pi over 4. Okay. Tangent is also positive in the third quadrant. So we want to find something that's in that pi over 4 family. Third quadrant, my numerator is going to be 1 higher than my denominator. So 5 pi over 4.
That one, can you just look at the table and see where sine equals cosine?
Yeah, that's perfect as well. Yeah, you can also look at your circle and realize, oh, pi over 4 is where root 2 is equal to root 2, and same in the third quadrant, right? So that's perfectly fine. You're able to look at your circle, but algebraically, you can also solve it using tangent. Good. Okay. I'll leave the rest for you guys to try on your own as part of homework. But I'll send out a reminder this weekend, and I'll also make sure that you know where to find the solutions. It's on my chapter P page where my videos are, and you're going to find this under today's date, today, Friday. I have this P4, P.4 miscellaneous worksheet. Okay, let's look at some equations of lines. So let's go down to the bottom half of page 14. Okay, I think A and B is pretty straightforward. Point slope form. All right, if you have your slope in your order pair, you can build your tangent line equation, or sorry, your equation of your line there. Given 2 points, you can build it starting using your slope formula. I think we did that, right? Okay, so we did that already. I'll have you guys try that on your own. Let's do C, perpendicular and parallel lines. Part C here. Okay, so part C says, given the point -1, -2, and we want the line perpendicular to this other line, y minus 2 equals 3, x plus 1. So the thing to keep in mind is the only thing we care about from this line is the slope. Okay? And once we pick out the appropriate slope, then that'll be our m. And then we have our point, and then we can put into point slope form. So it feels more complicated because they're giving you this information, but really we just want to pull the slope information from this line, and then once we adjust it to being perpendicular, we can use that information. So all this is just to get to the slope of my new line. Okay. But to get to my slope here, let me clean this up a little bit. Well, actually, this is in point slope form, right? So that's not too bad. What's the slope of this line? 3, right? So I'm going to say m1 equals 3. So if I wanted something that's parallel to this line, then I'll use 3 because I would use the same slope. But perpendicular means I got to make an adjustment, right? What adjustment do I need to make if I want a slope that is perpendicular to a starting one? So I'll call it M2. You guys remember the formula there? Okay, it's opposite reciprocal. Okay, so that means we got to do 2 things to that number. We have to change the sign, and then we have to produce a reciprocal of it. So what's the opposite reciprocal of 3? Negative what? 1/3. Yep, negative 1/3. So I have my new slope. I have my point, and then from there, I'm able to do point slope form. Hey, part D, same idea. You have a point, And then, but now we want something that's parallel to this line. So if we can find the slope of this line, then we can keep it and use it for my new line. But the challenging thing, the challenging here that we haven't seen before is that the slope is not easy for us to pick out just by looking at it. We may have to put it in a different form to get the slope. This is a point slope form, so that's fine. So, but this we may just want to solve for y, maybe get it into slope intercept form. So we clearly see that y equals mx plus b. So let me solve for y here to help me see the slope of this line. Hi. She's not here, but she may be running late. Okay, go ahead. Sure. Thanks. Okay, so I'm going to solve for y here. So 2y equals negative 3x plus 1. Divide everything by 2. So it's a little bit easier to identify the slope here, right? What's the slope of this line? Negative 3 over 2. So now if you look, this is the slope that we want to keep because there's no need to change it. We want something that's parallel to it. So if it was perpendicular, then we will make it positive 2/3, but this is the slope that we want to use. Okay. So now that we have our slope and our point, we'll do point slope form. Again, the reason that that we emphasize point slope form is because it's the easier one to get to, not because it's any better than slope intercept form. It's just it's more efficient to get to it, and if College Board accepts it, then we're going to choose the more efficient path. All right, any questions here? It says slope intercept form, but if you, I think it's easier. Yeah, if you can just make it point slope form. That's less work to get to, I think. So this is pretty straightforward, right? You use slope formula to get to your slope, choose either point and then point slope. So I'm going to skip 6. I think that's we've seen enough of that here for us to do. 7, same process. You get your equation to show you the slope, and then from there you either do parallel or normal. Normal just means perpendicular. Again, to do perpendicular, you just do the opposite reciprocal. Number 8, I think, is also pretty straightforward. Let's do number 9. So number 9 feels a little bit more challenging because there's that K that looks more. So I'll walk us through that. So I'll walk us through number 9. Okay, it says find K if we want the two lines to be parallel. And then find K if we want the two lines to be perpendicular. So what if we get both of these into point into slope-intercept form. And the reason sometimes we want to do slope-intercept form is it shows us the slope a little faster. So basically, it just means solve for y, right? If I can just solve for y, I can get the two for me to match the forms a little bit easier. So I'm going to spend the time just to solve for y for both of these, just to kind of see what that relationship is. Okay, so I'm going to play with this first equation. Second equation. Okay, now k is a constant, so I'm going to divide everything by k. I'm just trying to get y by itself. I'm able to kind of match these up a little bit easier now. So if I want parallel slope, if I want these two lines to share the same slope and be parallel, that means 3/5 must be equal to what? -2/k, right? So if I set these equal to each other and solve for k, then I can figure out what k value will allow these fractions to be the same. So that's part A there. Solving for k just by setting that 3/5 equal to -2/k. A cross multiply. So if I replace k with -10/3, then this fraction will turn into 3/5. Part B, if I want a perpendicular relationship, that means I need 3/5 to be equal the opposite reciprocal of -2/k. So I'm going to make that relationship here. So 3/5 is equal to the opposite reciprocal of -2/k. So what's the opposite reciprocal of -2/k? K/2, right? I changed the sign and I flipped that fraction. Okay, cross multiply, solve for k. So if k is 6/5, that will allow this to turn into a slope of -5/3. Okay, next page. We talked a little bit about condensing and expanding logs. So I guess some more practice here. And so if I want to condense, I'm basically trying to get all these logs to be multiple logs to be just one single log term. So let me go through the process here. What we can do is try to push every coefficient up as exponents. Nothing to do with the first term, but the second term, I can push that 5 up. And now I can use product property. If I have log of A plus log of B, I can make it log of A times B. So 3 times 3x to the 5th. As far as we need to go, we're just trying to merge multiple log terms into one log term. Okay, let's do part C. Natural log of 2 plus 4 natural log of x minus 3 natural log of y minus natural log of 8. So first thing is let's push all the coefficients up as exponents. Now, rather than combining them one at a time and say, okay, I see a plus sign, so I'll make a product, minus sign, I'll make a quotient. I think an easier way to just identify where all those pieces go, because really we just want to know where does the 2 go, where does the x go, where does the y go, where does the 8 go. So, but you see a bunch of plus and minuses in place. So just do this, the natural log of, create a big parentheses, and then you're just going to place your values in the numerator or denominator, depending on whether it's part of a positive or negative expression. So 2 is part of a positive log expression, so I'll just place the 2 up in the numerator. X to the 4th is part of a positive natural log, so it's going to stay up top. Y cubed is part of a negative natural log, so just put in the denominator. 8 is also part of a negative natural log, so put in the denominator. So just make sure that you don't put any plus or minus inside the parentheses. So the plus and minus is all going to be represented as a product or a quotient. So there's a little bit of cleanup that I can do. The 2 and 8 can reduce. So using this as an example, try part D, see if you can go through those same steps. So we push all the exponents up, all the coefficients up as exponents. And then the 4 squared is 16, so that goes up top. X to the 1/2. I can rewrite it as square root of x. You don't have to. You can leave it as x to the 1/2 if you want. Leave it in the denominator, so that's up to you. Y in the numerator, and 2 cubed, which is 8 in the denominator. Okay, so the flip side is expanding. So expanding is where we take an individual log and we just string them out so that every term is part of a positive log or part of a negative log. Okay, so let's try number 11. Let me do part B and D to walk through with you. So So I have log of x cubed minus, or log of x cubed divided by 9y squared. So maybe easy way for you to understand how to expand is that every numerator is part of a positive log and every denominator is part of a negative log. So if you can think of it that way, just like how we did above here, you don't have to split them up one by one, just do it all at once. So when we expand, we also want to pull any exponents down in front. Okay, so the 3 can come down, the 2 can come down. Okay, part D. Now, if you see that there's a plus or minus within the logs, we cannot expand those. Okay, so understand that we can separate the numerator and denominator, but these individual terms are not separable. Okay, we can't say, oh, this is natural log of 3x squared plus natural log of 1. Anytime that I have a plus term inside my log, it's stuck the way it is. Okay, so that that is a potential point of confusion that students have, is that if I have natural log of AB, I can expand that into natural log of A plus natural log of B. But if I have natural log of A plus B, we cannot do the same thing. Right. And students ask, well, what do I do? You have to leave it alone. There's not anything that you can do if it's in this form. We cannot expand that. We just have to work with what that form is. But if it's in the A times B, we can expand. This is stuck, and we just have to kind of go with this form and move forward. Okay, so I have a numerator and denominator that can separate. Numerator will be part of a positive natural log. The denominator will be part of a negative natural log. That's as far as we can go. We cannot, quote unquote, distribute the natural log through. Okay, this is inside the natural log expression. We can't distribute the natural log through. This is as far as we can go with expanding. And now there's also the selected chapter P problems, which I have a full solution printed out for you there. But let me see if there's any that I want to go over with you here. And so I think these may end up being a duplicate of a previous problem, but just work through those. Yeah, let me walk through some of those problems on page 18. How's that? So page 18. So page 18 says, find the value of f of x plus h minus f of x for each of the following functions. F of x equals 3x plus 7. So what we do here is we're going to find a substitution in and basically get the numerator out of function notation so that we can actually work with it. Because right now we have to find an appropriate substitution for the numerator so that we can actually clean this up. Now, f of x is ready to go, right? F of x is 3x plus 7, so I can make a simple substitution there. Now, f of x plus h is what we need to make sure that we can build correctly. Okay, so we talked about on the first page of notes that we can build an f of x plus h by creating a reserved spot from my f of x. So if I have f of x is equal to 3x plus 7, I'm going to reserve a spot. So wherever I see a x, I'm going to create an empty parentheses for the new argument. So now what can I put inside the set of parentheses? What's my argument that I want to build? X plus h, right? So I'm going to replace every parentheses with x plus h. So now this is my appropriate expression for f of x plus h. So now I'm just going to make my substitution here. F of x plus h is this new expression that I found. F of x is the original expression divided by h. Now, what do we have to be careful about when we put this 3x plus 7 over here? Can I do this? Parentheses, yep. So this minus sign is going to supposedly influence everything that comes after it. So if we don't put a parentheses, we're going to forget that this plus sign is going to end up changing. So put a parentheses there. Now let's clean this up here. Distribute the 3 through, distribute the negative through, combine like terms. X is canceled out, 7 cancels out. I'm left with 3h over h, which can further reduce to just 3. Now, not every problem is going to allow all the h's to go away as cleanly as that, but you're just going to reduce as far as you can go. Okay, you guys want to try part B, see how far you can go with the exact same process that we did for part A. It just feels a little bit longer because there's going to be a little bit more cleanup that's required. And so the hardest part is just building that f of x plus h, right? Making sure that we don't put the x plus h in the wrong spot. So I always like to start off by just making sure that I have a reserve spot for where my argument's going to go. So I'm just going to rewrite my original function and put parentheses around all my x's. And then that will tell me exactly where my x plus h will go. So my x plus h will simply go inside all the parentheses that's been where x used to be. Okay, so now we're just going to place it all into my numerator expression here. So we have to first start off with f of x plus h. So I'm going to take that numerator and replace it with this whole expression here. So this will go in for that f of x plus h minus big parentheses, and then you're going to put your original expression after that minus sign. Okay. So this whole thing is my f of x plus h. Let me show a cleaner version of this. Right, there's my f of x plus h minus parentheses f of x all over h. Okay. I didn't go past this in terms of cleanup, but let's just continue cleaning up. We can FOIL, expand this out. So make sure you don't do 3x plus h and then squaring it. The exponent comes first, right? PEMDAS. So we got to FOIL and expand the x plus h first, and then distribute the 3. Make sure that you also write this x plus h twice, and then you square, and then you expand. Don't just make this x squared plus h squared. You're missing out a middle term if you did that. Right? So we got to do x squared plus 2 plus xh plus xh plus h squared. So this is my expanded version of x plus h. This distribute the 3 through, distribute the negative through, distribute the negative through. And then a lot of terms will cancel out. Right. Then we take our remaining terms. And we put them here. 6xh plus 3h squared minus 2h all over h. Notice the numerator does have a GCF that we can factor out. They all share an h. We factor that h out. Then we can make it go away with the denominator matching the numerator term. And then we have 6x plus 3h minus 2. That's as far as we can go. No more like terms. That's our reduced expression. Okay, part C. See how far you can get in terms of setting it up. And there is going to be common denominators that's required to help us get through. So I'll walk us through that, but see if you're able to at least get it set up and put the x plus h in the right place. So this is my f of x plus h. Right? I have my parentheses there. So that reserved spot is where my x plus h goes. So here's my f of x plus h minus f of x all over h. Now, the way I clean this up is I have to clean this portion up first. Let's try to get that numerator portion to merge into one fraction, but to merge it into one fraction, I got to have common denominators, right? I can't subtract or add fractions unless the denominator is the same. So let's just work on getting that to clean up. So I'm going to focus on this portion here. What's my common denominator for those two fractions? Now, these are different, right? These are completely different from each other. So I need both of them to create my common denominator. We can't say that x is part of x plus h. They're completely different. So we need both of them. So now that we have common denominators built, we have to decide how can we balance each of the numerators. So what's changed between this old denominator and this new denominator? X, right? So whatever has been added need to be included in the numerator so we can balance the numerators out. So I needed x in the numerator to balance out that change. And what's changed between this old denominator and this new denominator? X plus h. So we need to also include an x plus h in the numerator to adjust for that change in that denominator. So once you're here, now we can merge it into the same fraction. Now we don't want to do this. We don't want to start canceling out, because if we cancel out, then we're back to where we started, right? The whole point of this is to get the denominators to be matching. That way we can merge it all into one fraction. So now this is my result of finding a common denominator. So what started off here, common denominator, now we're able to merge it into one fraction. I distribute the negative through. I can still clean up that numerator here. The 6x's cancel out. Okay, so we're getting closer. At least we're able to get that numerator portion to merge into one fraction. It's still a complex fraction, but all we need to do now is to find a way to get this h to shift up to the top so that we can actually just clean this up. So dividing by a denominator or dividing by a value is the same thing as multiplying by its what? Reciprocal. So the reciprocal of h is simply 1 over h. So I'm going to just bring that 1 over h up to the top. I know this goes away, so I'm just having to worry about how to clean this up. Now, this is basically a fraction times another fraction. Notice my h's are clearly above each other, so that's a candidate for me to just cancel out. And that's as far as I can go in terms of reducing. So negative 6 over x times x plus h. Now there's meaning behind this notation that we haven't gotten to yet. When we get to unit 2, limit definition of a derivative, we're going to see what this means. But the reason why we're doing this now is so that we can kind of get used to all the algebraic stuff that comes on the back end, so that we can just focus on the concepts later on. Okay, so you guys have homework over the weekend to finish off the entire packet. I'll send out a reminder on Sunday, and then I'll be checking your packet on Monday. Okay, come get your phones. Guys, to make it more efficient, I may just have you guys turn in your packet so that I'll just check through it and I'll give it back to you. So make sure you put your name at the top of your packet. but I'll send out a reminder this weekend so that, you know what the process is on Monday.